So, good evening, and we will look at the last part of natural convection today. So, before we move on to turbulent convection. So far we have focused on the methods to obtain analytical solutions through similarity methods or approximate methods, like such as the square solution, and all these have been focused on a very simple vertical flat plate configuration. Okay. So, now what happens if we deviate from this plane configuration? We will see that it is not possible to get analytical solutions for more complex geometries. So, we will quickly go over some of the other configurations, and I will give you the empirical correlations which have been obtained through experiments, and maybe you can just use them whenever you solve natural convection problems involving complex shapes. So, one deviation from the simple vertical flat plate is that if you tilt the plate, so let us say that this is your plate here, okay, and your gravity is of course acting downward vertically, and let us say you have an angle theta with respect to the vertical direction. So, this is the tilt of the plate facing downward. So, if you heat this plate such that T ball is greater than T infinity, still the same natural convective boundary layer will form, but the only difference is the strength of the gravity will be slightly reduced in this case. Okay. So, the same governing equations will be applied. For example, if you denote this coordinate as x along the plate and perpendicular to the plate as y, you can still write down the momentum equation. This is the momentum equation along the plate length. This is what we call as the x moment, and we have nu d square u by dy square, plus the only difference here is that we have cos theta multiplied to g. Okay. And the energy equation is still the same. Okay. So, therefore, in such a case we can have the same solution whatever we did for the vertical flat plate, and we will only redefine the definition of Grashof number. Okay. So, we will just include g cos theta into beta T wall minus T infinity into x cube by u square. So, we will just include the inclination angle cos theta directly into the definition of Grashof number. So, that whatever solution that you already encountered, whether it is the similarity solution or the approximate solution, is still valid for this case with the slight modification in the Grashof number. Okay. So, but now we have to be careful that if you have a limiting case where you tilt it facing upward, that is your theta in the minus direction, and you make it minus pi by 2. Okay. So, what happens? So, when you have a configuration where you tilt it this way, so that is the plate is facing upward instead of downward. What happens when you tilt it such that theta becomes minus pi by 2 in this direction? It becomes a horizontal plate. Okay. So, you will have a heated plate, position horizontal, gravity acting downward. Okay. So, can we use then the same equations here? So, you have x and this is your y. The limiting case where your theta becomes minus pi by 2. So, you have a horizontal surface. Now, can we still apply the same equation to this configuration? We cannot, because as you see the buoyancy is now acting in the y direction. There is no buoyancy at all in the x direction. So, therefore, we have to be careful, okay, for reasonably small inclinations. The earlier approach is okay, but if you have a completely horizontal plate, then we have to redefine the governing equations. So, in that case, what will be the x momentum? Okay. So, in this case you cannot include the Boussinesq approximation in the x momentum, because there is no gravity in the x direction. So, you just write your boundary layer equations. So, this will be your x momentum. Now, the effect of buoyancy will be felt in the y momentum equation. Okay. So, therefore, although you neglect the y momentum in the advection part, there will be a pressure gradient in the vertical direction, which will be balanced by the buoyancy force. So, this will be equal to therefore g beta into T minus T infinity. So, this is the modified set of momentum equations for the horizontal heated plate configuration. Okay. So, for this also we can find some similarity solutions, which I am not going to go through in detail, but I will only give you the final expression for the Nusselt number. This was done by Pern and Gebhardt, PERN. So, this is Pern and Gebhardt, and for the isothermal case they have given the following. So, this is coming from the similarity solution 0.5013 Grashof number to the power 1 by 5, Prandtl number over 1 by 4. Okay. So, to derive this they used a similarity variable eta, which was y by x Grashof number by 5 the whole raised to the power 1 by 5. So, this is the kind of similarity variable that they used. Okay. So, you see that the advection component, the momentum is neglected, but in this case you do not have dP by dy is 0. So, you have the pressure gradient in the vertical direction balanced by the buoyancy force. Okay, whereas in the axial direction you do not have any buoyancy force, but the most dominant momentum will be in the axial direction. So, this is the kind of configuration which is different from what we have seen so far. So, now all these are assuming that the plate lengths are infinity, right. So, what happens if you talk about finite plate lengths? So, if you for example make this finite, so then you have edge effects coming into picture. Okay. So, let us discuss this configuration, which is also kind of common. So, this is the case of horizontal finite plate in the horizontal direction. So, we have a case in which we keep the plate in the horizontal configuration and this is finite in length. Okay. So, one case A, we heat the plate, okay, and we can have case B where we cool the plate. That means T wall is less than T infinity.
In the case of horizontal plate, isn't the velocity in y direction equally prominent?
Yes, but in the most important component which is governing the variation of Nusselt number along the x direction is your momentum in this direction. As you can see, the Nusselt number here is calculated as a variation along the plate length. So, therefore, it is actually the axial momentum which is the reason why the Nusselt number is itself varying in that direction. So, it has been made an approximation that we can neglect the y momentum in the advection part and we can still solve this to get the profile variation, the variation of the u momentum in the x direction which actually influences this. But this is an approximation. Of course, you can you have to do a finite difference or finite volume method based solution in order to solve this exactly. You cannot neglect also the vertical momentum. There will be some patterns, streamline patterns which will rise due to the buoyancy in the vertical direction and that will definitely cause some vertical momentum. But while deriving the similarity solution, it has been assumed that that is not going to impact the local heat transfer. Okay. So, of course, we have to make some assumption in that case. If you also include the vertical momentum, you cannot find a similarity solution, right. So, let us come back to the finite plate configuration where T wall greater than T infinity. Now, what do you think will happen when I have a heated plate and surrounding is T infinity and this is finite length. So, naturally the fluid in contact with the plate which is getting heated up has a lower density and its tendency will be to rise up. So, therefore, since now you have a finite length, so this will try to sneak in through the edges of the plate and this will be symmetric from both the edges. So, if you draw a vertical line, so you will have a symmetric patterns in the flow about this line. So, you will generally see that. So, this is the kind of patterns that you will end up. Okay. So, that is the hot fluid which is in contact with the plate at the bottom surface will now have a tendency to escape through the edges. If this was infinite, so this hot fluid will be just staying there, it can never rise up, but due to the finite length, so the edge effects now cause the flow of the hot fluid to rise up and also the hot fluid on the top surface, what will happen? So, this will also have a tendency to rise up. Correct. So, this is a very complex flow pattern that you will have. Okay. So, in this case you cannot neglect the y momentum. So, everything will become important. So, therefore, you cannot find analytical solution. Now, what is the case where you cool the plate? So, in this case again the density of the air surrounding the plate will be heavier compared to the ambient density. So, therefore, what is the tendency? It should be the reverse, it should try to come down, sneak downwards. So, therefore, if you draw a vertical line, so about that you have a pattern which is something like this. And at the same time, the heavier fluid at the bottom surface here will also tend to move downwards. So, in one way the flow pattern at the top surface of the heated plate and the bottom surface of the cold plate are identical, and vice versa. And the flow patterns in the bottom surface of the heated plate and the top surface of the cold plate are also identical. Okay. So, therefore, the empirical correlations have been developed for one pattern which is this one, the other pattern which is this one, and the same pattern for this can be used for this also, and similarly the Nusselt number for this pattern can be used for this also. So, now obviously you should understand that the Nusselt number for the top and bottom surfaces will be different because the flow patterns are locally different. Okay. So, I will just give the correlation. These are obtained from some experimental observations. Okay. So, let us identify this region to be so I will call this as region 1, region 2 here. So, that is region 1 is the upper surface of the heated plate, region 2 is the lower surface of the heated plate, and 3 is the upper surface of the cold plate, 4 is the bottom surface. So, for regions one and 3, so these 1 and 4, so these are identical flow patterns. So, the average Nusselt number based on the length of the plate. So, you can call this plate length to be some capital L. This is calculated as 0.54 times Rayleigh number to the power 1 by 4. Okay. So, how do you now, so far we have not defined Rayleigh number, right. We have used everything in terms of Grashof number. So, we will define Rayleigh number. Now, Rayleigh number is nothing but another non-dimensional combination of Grashof number into Prandtl number. So, many a times you see that Grashof number, Prandtl number come together. So, many times you can kind of see that in some complex configurations the power of Grashof number and Prandtl number might be identical, such as this case. Okay, both Grashof number and Prandtl number raised to the power 1 by 4. So, in that case they can be grouped and you can have one single non-dimensional number called the Rayleigh number. So, this will be nothing but G beta delta t. So, now if you define this based on the plate length, this will be L cube by nu into alpha, right. There is the product of Grashof and Prandtl number. So, similarly for regions 2 and 3. So, region 1 and 4. So, region 1 is the upper surface of the heated plate, 4 is the cold surface for the bottom surface of the cold plate. Now, for regions 2 and 3, that is the bottom surface of the heated plate and upper surface of the cold plate, we have again identical flow patterns. So, therefore, we have another correlation for that. This is given by 0.27 times Rayleigh number raised to the power 1 by 4. Okay. So, this region 2 and 3, so they seem to have a smaller value of heat transfer rate compared to region 1 and 4. Okay. So, these are some correlations for a more complex configuration like this. We can also look at other configurations. For example, the case of a heated cylinder, okay, heated cylinder which is just suspended in the ambient where T wall is greater than T infinity. Okay. So, in this case how does the flow pattern look? So, again you will have something like this. Okay. So, you have rounded edges now instead of the sharp corners here. So, therefore, the heated fluid will tend to rise up due to buoyancy and you will get nice flow patterns looking like this. Okay. So, from the upper surface you also have some flow patterns which are rising up. So, similarly for cylinder also, similarly for sphere, this is cylinder. So, that means you do not have any variation in the depth. So, it will be uniform within the perpendicular to the board, but if you look at sphere there will be variation in the third direction as well. Okay. So, but nevertheless if you take a cross section of that you will find a similar onion bulb kind of a flow pattern. So, for these there are some correlations available. The most comprehensive correlation was developed by Churchill and Chu. So, this is the most commonly used correlation and this is valid for Rayleigh number. Now, in the case of cylinder and sphere, the Rayleigh number is based on the diameter. Okay. So, this is valid for a Rayleigh number greater than 0.1 and less than 10 power 12. That means a very wide range. So, 13 orders of magnitude variation. So, this has been correlated over a wide range of experimental data. So, this is one of the most popular correlations. It is a very complex looking dependence on Rayleigh number and Prandtl number, but this is the same kind of formulation which is also done for the vertical flat plate, because as you can see the vertical flat plate whatever we have done so far is for laminar flows. Now, if you want to extend it to turbulent flows, again we cannot use the similarity solution. So, the same people Churchill and Chu, they have developed an empirical correlation for wide range of Rayleigh numbers. So, I will also give you their correlation for vertical flat plate which is of the same form. So, for vertical plates, so this is valid for Rayleigh number from 10 power minus 1 to 10 power 12, and this is the correlation for the average Nusselt number based on the length of the plate, not the local Nusselt number. This is something similar form, instead of the 0.6 you have 0.825, but this also is the same. This becomes 1 by 6 here divided by 1 plus 0.492, Prandtl number 9 by 16, 8 by 27. A very similar form to the cylinder case, some small coefficients are slightly different, and RAL is raised to the power 1 by 6, whereas there it is raised to the power 1 by 2. So, again for general heat transfer calculations, this is very accurate for a wide range of Rayleigh numbers, all the way from laminar to turbulent, right. And in the laminar regime, this will be recovering the correlation by Ostrach. Okay. So, this will agree very well with Ostrach solution. Now, for sphere, for the case of sphere, we have a simpler correlation which is fairly accurate. 2.2 plus 0.43, again Rayleigh number based on the diameter of the sphere, but this correlation is valid only in the laminar regime. Okay. So, let me just quickly check its validity, because this seems to be quite small Rayleigh number range. So, looks like this package does not have, yeah, there is, yeah. So, looks like this is valid for a small Rayleigh number regime, that is correct, so less than 10 power 5. Okay. We do not have a very accurate correlation for sphere for a wide Rayleigh number range. Okay. So, these are some common complex configurations. So, you might encounter anything close to a cylinder, you can use the cylinder, and 3-dimensional object you can use a sphere, and so on. So, kind of with these kind of correlations you can approximate slightly more complex surfaces, and you can apply these correlations. So, next what we will do is quickly look at the presence of natural convection in internal flows. Okay. So, all these have been on external flows, there where you place a plate in a free stream and you observe the buoyancy forces which aid the development of the boundary layer. Now, what happens when you confine this completely? Okay. So, that means you can look at simple objects like cavities, and where you do not have per se anything like a external free stream temperature and density. So, what happens to these natural convection boundary layers within enclosed spaces? Therefore, there is a separate discussion on natural convection inside enclosures, and in fact these are far more interesting than the external natural convection, because external natural convection we are doing in detail because of the availability of solutions, but the more interesting phenomena occur when you have natural convection in cavities. So, one of them is that you can have two parallel plates in 2D configuration. Okay. You can, for example, heat the bottom plate and keep the top plate cold. Okay. And what happens now, again due to the buoyancy forces. So, this will be an unstable configuration, the bottom plate will heat the air and the top plate will cool the air, and therefore, the tendency will be to rise up and this will be to descend downwards. In the end, you will be getting some kind of structures, vertical structures like this, where the hot fluid tends to rise up, cold fluid will come down, and this can happen symmetrically. Okay. So, depending on therefore, the length to the height ratio. So, the aspect ratio of this configuration, you can have several number of these vertical structures appearing. So, this kind of vertical structures are attributed to what is called as Rayleigh-Benard convection. Okay. So, essentially this is happening due to an instability. That means if you say this is your y, so what should be your d rho by dy? Should it be positive or negative? It should be positive. So, then only this can be a unstable configuration. Now, what happens if you heat the top plate and cool the bottom plate? So, in this case what will be d rho by dy? Negative. So, what do you think will happen in this case? This will be a stable configuration. Okay. The heated fluid will be stratified here and the cold fluid will be here. Okay. The stratification will happen, the hot fluid will stick to the top surface, cold fluid to the bottom surface, but you will not have any of these convection patterns. So, this is a stable configuration and no convection cells will be formed, right. So, in order to produce the Rayleigh-Bernard instabilities, you need to have unstable configuration where d rho by dy is greater than 0. So, this you can very nicely see the vortical structures happening, and you can also see this in 3 dimensions. In 3 dimensions you will see a honeycomb kind of a structure.
So, in this case also the inverse of it should happen, right? That is from TH to TC there must be
correct, but TH, the lighter fluid will be only can rise up, it cannot go down. So, therefore, you cannot have a convection from the hot to the cold in that case. Okay. So, it will always, this is always buoyancy aided convection. Okay. So, you cannot have a convection which is opposing the buoyancy and going, only the buoyancy has to aid it. So, the natural direction for buoyancy to aid is d rho by dy greater than 0, right. So, for this case these are very complex instabilities and you can to some extent do some linear stability analysis and predict the onset where the instabilities can become Rayleigh-Bernard convection cells, but beyond that you cannot use any analytical methods. Okay. So, these are usually predicted by numerical methods. Okay. You have to solve the entire set of Navier-Stokes equation with the Boussinesq approximation and you will be able to capture this kind of roles, convection roles. So, I will not have a very detailed discussion on this, these are topics beyond the regular classroom thing, but the other interesting configuration in 2D is to have an enclosure, that is a cavity which is closed on all sides, okay, and you can heat the left wall of this cavity and you can have a cooler right wall, the top and bottom being insulated. Okay. So, this is another interesting configuration. Okay. So, now what happens when you have a differential heating between the left and the right walls? Again, so you will have a boundary layer which can actually grow, okay, and again a boundary layer which will descend in this direction. So, what will happen together in an enclosure will be, the net effect will be a vorticity which will be driving a convection cell in this direction, the clockwise vortex. Okay. From the hot side it can only rise up and from the cold side it can descend down. So, you will be ending up with a clockwise vortex pattern. Okay. Now, very small temperature differences. If you define, for example, Rayleigh number based on this temperature difference between the left and the right walls, and let us say the cavity is a square cavity with sides dimension h. So, for small Rayleigh numbers less than say 10 power 3, in this case the temperature difference will be too small to produce a convection pattern. So, it will be only conduction which has happened. Okay. So, therefore, when you look at the isotherms, you will find that there will be simply a linear variation from the hot temperature to the cold temperature. So, once you increase the Rayleigh number above 10 power 3, that is when you find the non-linearities in the isotherms. So, the isotherms will now start deviating like this. Correspondingly, you will find this vortex pattern appearing. So, as you keep increasing your Rayleigh number, you find the vortex pattern becomes more complex. You might get more than one vortex there. Okay. And what will happen to your Nusselt number? There is Nusselt number on these two walls, they will increase with your Rayleigh number. So, as your Rayleigh number increases, your Nusselt number also consequently increases. It increases the convective motion and therefore higher heat transfer rate. Okay. Now, this is again we can find the solution only by numerically solving the equations, Navier-Stokes equations. Okay. So, what I suggest is that this is a very interesting problem for you to solve the equations as such. So, I would suggest that you follow the solution procedure as given in this book by Oosthuizen and Naylor, Convective Heat Transfer. Okay. So, I will give you also the section number where he has explained the complete numerical solution to this cavity problem. So, he has given a wonderful explanation, section 8.9, that is chapter 8.9 in chapter 8, natural convection. So, the topic is natural convection heat transfer across a rectangular enclosure. So, there he has listed down the equations, the boundary conditions, and also how he is solving them with finite difference methods. So, this is introduction to convective heat transfer by Oosthuizen, Patrick Oosthuizen and David Naylor. Actually, I think this is an e-book now which is available for free. I think most of you can, all of you can access this. This is an open access e-book. Okay. So, this is available on the, if I remember right, this is part of the open access thermal fluids, the thermofluids, they have an open access of journals and books. So, you should thermofluid central it is called. Okay. So, thermofluid central, if you go to their website, they have some free open access e-books. And although originally it was published as a hard copy, now they have a free e-book as a soft copy available which you can download. Okay. So, especially you look at this section, he has very nicely shown the way he is solving these equations is by what is called the stream function vorticity method. So, rather than directly solving the continuity and the momentum equation, because if you use stream function, it makes the continuity equation redundant. So, therefore, rather than having so many equations, you have only two equations, one for the stream function, the other for vorticity, right. So, you introduce the definition of your stream function d psi by dy, V is equal to minus d psi by dx, and similarly vorticity, which is dV by dx minus du by. So, this is then cast the equations, the Navier-Stokes equations, both the x and y momentum are then rewritten. Okay, we do some manipulation there, like for example we take the derivative of the x momentum with respect to y and y momentum with respect to x, and then we subtract. So, we can actually recast these equations in terms of a vorticity equation, and since the stream function satisfies continuity, okay, so we will have a simple stream function vorticity equations which can be solved, and the appropriate boundary condition and the procedures are all very nicely explained. So, you can just go through and he is using only simple finite differences. I am sure most of you would have already gone through some numerical methods course. So, you should be able to quickly understand how to solve the finite difference equations. Okay. So, you can use an iterative scheme, for example like Gauss-Seidel, okay, and try to find the solution. So, it is a very interesting problem because once you code it, so you can change the Rayleigh numbers and you can look at the different streamline patterns. So, I suggest that you please take this up as part of your final project. Okay. Look at Rayleigh numbers in the range from 10 power 2, okay, till 10 power 5, that is 3 orders of magnitude variation in the Rayleigh number, and you can actually use the following correlations to compare your numerical solution for the Nusselt number. You can assume that your Prandtl number is equal to 1, okay, and so for the Rayleigh number between 10 power 3 and 4, this is the correlation, and for Rayleigh number between 10 power 4 and 6, the correlation becomes 0.065, Rayleigh number or 1/3. So, you can actually try up to 10 power 6 if you can run the code. If you cannot run up to 10 power 6, you can stop it till 10 power 5. Okay. So, you run the code, get the results for Nusselt number and compare it, plot them as a function of Rayleigh number. So, your average Nusselt number as a function of Rayleigh number. So, you plot your numerical results and also the correlation. You should be able to match very close, and also you can look at the streamline patterns. You can plot the streamlines because already you are solving for the stream function. So, in MATLAB you should be able to plot the stream function, isotherms, all this for the different Rayleigh numbers. Okay. So, yeah, so this is a very interesting exercise of all the things that we have done in forced convection and so on, because you see flow patterns which vary drastically with the changing Rayleigh number. Okay. So, so please try to submit this project when you come for the final exam. Okay. So, that will be mostly I think 3rd May. 3rd May is the D slot exam. So, we will have the submission of the project also on the same day, along with your final assignment. The final assignment I have posted. It has both natural convection and turbulence. Turbulence we will be covering in another 4 classes. So, meanwhile, so you will have time to work on the natural convection part. So all this together, the assignment which I have posted, assignment 5 and the project together on the day of your end sem exam. Okay. So this is a very standard problem. If you go through some literature survey, you should be able to find many papers to validate, and programming is given very nicely explained in this book. Okay. So any questions? So in that case we will conclude. One last topic which I would talk very briefly, a few minutes, is the case of mixed convection. Okay. I have mentioned about this in the beginning of the natural convection part, but I want to just emphasize, because most of the practical heat transfer problems are having the combination of both natural and forced convection. You cannot ignore either of them. So in that case, what happens to the flow patterns? So for example, if you talk about gravity acting downward and you have a forced motion, bulk motion of fluid, and along with that a natural convective boundary layer. Okay. So this is one case. The other case where the buoyancy is acting upward, but the forced motion pushes the fluid downward. Okay. So in this case you will have a boundary layer growth. Okay. You should understand that since there is a forced convection motion in the upward direction, so this will kind of tend to compress the boundary layer compared to the case where you push the bulk motion downwards. So in this case the boundary layer will look more stretched out. Okay. So when we do these kind of flows, now what is the way to calculate the similarity solution? Is there a similarity solution for this problem? Well, the thing is, what is the correct similarity variable to use, because when you talk about forced convection boundary layer, we use the Blasius variable, but natural convection involves Grashof number. So which similarity variable can we use to describe this problem? So therefore if you look at the cases where the ratio of Richardson number, that is your Grashof by Re square, is of the order of 1, we cannot find any similarity solutions because both of them are very dominant. But for the limiting cases, for very small Richardson numbers, okay, so there the forced convection similarity variable might be the correct one. And similarly, if you go to the other limiting case where Richardson number is basically very large, so there the Grashof number, using Grashof number in the similarity variable might give you the similarity solution, but these are only in the limiting cases. Okay, but most of the regimes where both are dominant, we cannot find any similarity solution to this. Again we have to go for numerical solutions. But as I told you, so the simpler way of doing this is to just blend the Nusselt number from forced and natural convection by using a simple power law expression like this. So wherever you have a forced convection which is assisted by buoyancy, so you use a plus sign, and wherever you have a forced convection opposing the buoyancy, you use a minus sign. So naturally the case where you assist the buoyancy will be the one with a higher Nusselt number, because you compress the boundary layer and therefore the wall temperature gradient will be higher. Correct? So this is a very simple hands-on approach. If you want a very detailed flow patterns, then you have to go for again numerical solution. So I will try to quickly cover the turbulent convection also. Okay, so I think it should be sufficient. Okay, so thank you very much, and please take note that you have to also complete the project along with the assignment when you come for the end semester, right.